This is Dr. Sirisha, working as Associate Professor in Institute of Aeronautical Engineering College. Today we are going to look at a few basic terms and features which we encounter in learning data structures. So what is the root of a data structure, and how many types are there, how to work with them? All these terms and definitions we are going to see in this video. Let's start with what a data structure is, the meaning, right? So the basic depth of data structure is it is a collection of raw facts arranged in an order, right? So data, let's split that word data structures into two halves. When we split it, data will be the first part, and it is a collection of raw facts. Whether it is right or wrong, it's a different story, right? Structure is nothing but extracting the useful information from the data and bringing logical relation between them and placing them in an order is nothing but a structure. And a cumulative of these two, data and structure, is a way of organizing the data in a particular fashion so that it can be utilized. Whether it can be inserted, data can be inserted, it can be appended, can be deleted, can be updated, can be manipulated in any way, right? Withholding the relations that are present in it is nothing but data structure. In an effective sense, you can say that a program, generally an executable program, is nothing but a combination of data structure and an algorithm. Okay, what are the basic operations that we perform on a data structure? Then the basic operations will be, we can, as I said, we can insert an element, we can delete an element, we can traverse through that, we can search for an element, we can reverse it, we can sort it. Many are there. All the basic will be the one which I have listed over here, the basic of few, right? So how these data structures are classified. They are broadly classified into two different categories. One is primitive data structure, the other is non-primitive. Coming to primitive data structure, we have integer, character, float, and pointers as the primitive data structures. Why we call them as primitive? Because the definition or the meaning of these terms is already been defined in the compiler or the interpreter on which we are working, right? For example, say integer. If you say that a variable is an integer, then the compiler knows that 4 bytes of memory is supposed to be allocated for that, right? And if we by force insert a float value into it, truncate the fractional part. So all these depths are hidden inside it, right? So they we can include the modules or header files relevant to that, and straight away we can use them, right? So such a data structure is nothing but a primitive data structure. Coming to non-primitive data structures, they are in two different categories. One is arrays and the other is lists. Let's go and understand what an array is. Array is nothing but storing the data in contiguous memory locations, right? So contiguous memory, and the data will be homogeneous in order. Okay, so if there are 10 elements, all the 10 elements will be placed one after the other in the memory. So in case of arrays, you can have a single dimensional array, which is also known as a vector, and two-dimensional array, which is generally known as a matrix also, and multi-dimensional. So in three different ways we can work with arrays, right? So the general, if you take the help of C language, the declaration will be what type of array you are talking about, the name of the array, and the maximum size it is going to take. With the basic initialization or declaration, generally you can say declaration of an array, okay, in C. Coming to lists. List E will be of two different categories. One is linear, the other is non-linear in nature. Okay, coming to list, what is a linear data structure then? So the linears are stack, queues, and linked lists. So why we call these three data structures as linear? Because every element in this type is related to only one another element of the same type, right? So for example, in a stack, we all know that in case of stacks, last in first out philosophy will be used. That is, the most recently inserted element can be picked out, right? Coming to queues, first in first out, the element which is first inserted will be removed first, right? So in both the cases, the elements are related to one another, and there is one-to-one cardinality. Coming to linked list, also the same point. Every node holds the address of the next node, only one node. So that's why we call them linear in structure. Coming to non-linear, trees and graphs are the best example for the same. So coming to trees and graphs, we know, we can understand that by the names itself, we can understand that here an element is related to more than one elements of its kind. For example, if I take a tree, this is the parent node which is having three children, and the first and second child is having two children. That is the root node is having two grandchildren, right? And the third child is also having a child. You can see that, say the root node is at 0, it is having three children, 1, 2, 3, and the second child is having two children, 4, 5. So the cardinality, the way they are related to one another, is not one to one. So such a structure will be a non-linear structure, and this is an example of a tree. If you look at graphs, let me give a small graph for you. So let me draw a small graph: A, B, C, D, and E. Here are the 5 nodes. Okay, so how they are related. You can see that A is related to B and C. Whereas if you talk about D, D is related to B, C, and E. That is, every node can be related to more than one node. So such a structure is non-linear data structure. So the best examples are trees and graphs. As a whole, this is the chart of classification of data structures, right? So let's move on. So we said that we have learned that a program is a collection or a combination of a good algorithm and a data structure as a support to that, right? Let us understand. We have seen what a data structure is. Now let us understand what an algorithm is. Algorithm is nothing but a stepwise representation of solution of a given problem. It will tell us how to perform calculations, how data is processed, and how it is automated reasoning task. All these things will be embedded in an algorithm. Okay, it is an efficient method of expressing the solution, and it is independent of any programming language. Remember, guys, algorithms are generic in nature. They are a kind of templates. If there is a problem, say sorting, to sort the data, using the algorithm, you can implement it using Python language, C language, Java, C++, Rust, any programming language. But the algorithm or the basic logic which we are going to represent in terms of algorithm, that is stepwise representation, is not going to change. How to analyze an algorithm? It will be analyzed based upon the worst case, best case, and the average case. So what are these 3 cases then? Then the worst case is, take the worst scenario. For example, let me take linear set as an example. Okay, simple example I'm going to take over here. Right. What is the worst case for this one? The worst case is a case where the element is not present in the list itself. the element which you are searching for is not present in the list itself. So that will be the worst case. You will be searching throughout the list, and at the end of the day, you will be realizing that the element does not exist itself. That is the worst case. Coming to the best case is a case where the first element itself is the element which you are searching for. The first element, right? So next, the average case is it is a collection of all the cases. Say, what if the element is the first element, second element, or the last element, and including the case which says what if the element is not present in the list itself, right? So a collection of all these cases is nothing but the average case of analyzing an algorithm. Using all these three, we try to evaluate or analyze the performance of any algorithm. Right. Coming to the basic properties of an algorithm. Finiteness, definiteness, generality, effectiveness, input, output are the 5 key features of an algorithm. Finiteness, the first one. It tells you that the number of steps involved in expressing the solution of a problem must be finite in nature. You can never say that you keep on doing these steps, taking these steps, and one fine day you'll get the result. No, the solution must be different, and it should be confined in a finite number of steps. Next one is definiteness. That means it should be precisely defined. Don't give unnecessary statements in an algorithm. Algorithms do not have that. Like user-friendly statements, kindly enter the data. All this stuff is not required in an algorithm. Algorithm is purely logical solution to a given problem. So please confine to your job. Each and every step you write in an algorithm must add some value to the solution, right? So next one is generality. So generality says that the solutions which are represented in terms of an algorithm must be generic in nature. For example, the problem is addition of 2 numbers. So your algorithm should not be in such a way that it will be going to help you out in adding only 2 integers, but not 2 float values or not 2 real numbers. If I go more precisely, right? It should be generic in nature. If the algorithm is written, it should be in such a way that when you convert that into a program using any programming language, you use that algorithm to add 2 integers, to float, or a combination of that also, an integer and float. It must work, right? So generality is the key feature of any algorithm. Next, effectiveness. So it must be effective in nature. If you must be able to write it with a pen and a paper in your hands, you must be able to put it, or you must be able to manually evaluate it, right? When someone learns any programming language, at the initial days, they will be tracing the program, right? Manually, we trace the program whenever we learn loops, for loop, say example, right? So initially, we try to trace it, how it is being executed, how it is initialized, how the variable which controls that loop gets incremented or decremented or updated, when I talk it in a generalized way, right? So how it is getting updated, right? So effectiveness must be there. You must be able to manually evaluate it, right? And next, the last property is input and output. The algorithm must take some initial or precise inputs, and it must give at least one output. At least one output must be there, right? So these are the 5 properties of an algorithm. So coming to the analysis, the performance analysis of an algorithm using time complexity and space complexity. These are the 2 key features using which we evaluate the complexity of an algorithm. Then what are these 2? Time complexity tells us about how much amount of time this algorithm needs to evaluate, gets to or give us the correct output, right? And time complexity depends upon the input which we feed, right? For example, for addition of two numbers. Say the algorithm is meant for addition of two numbers. Just don't give 2 plus 3, you got 5, give the clap, and time complexity is very less. Don't do that. Give a huge number, say a number which is having say 10 digits, both the numbers having 10 digits, and try to add them and see how much of time it is taking. Say example, any value which is power of 9 or power of 10. So take huge numbers and try to calculate. Only then the algorithm is going to show you its true colors, right? So whenever we calculate the time complexity, go for the best, average, and the worst case also, right? So a cumulative of that will give you the time complexity of an algorithm. Coming to the space complexity. Space complexity is nothing but the total amount of memory required to execute that program. For example, let me take an example of two sorting techniques. Okay, so quick sort and merge sort. So coming to the space complexity, quicksort will take very less space. Why? Because it maximum it takes a space of one or two variables, that to temporary variables, my dears. Temporary variables it is going to take hardly two. Worst case, I'm taking two variables. That's it. But for merge sort, you need an array which is equal to the size of the list you have taken, or the set of elements you have taken. That is the temporary array which is equal to the size of the elements you have taken. If you taken 100 elements, then you need to take a temporary array of 100, right? So merge sort is very costly when you evaluate it in terms of space complexity, right? It is the total amount of space required to work with that algorithm. Okay, so these are the two parameters with which we evaluate the complexity, or we evaluate the performance of any algorithm. Good. Then let us talk about different kinds of algorithms with which we can address a solution, right? One of the best one is, so you all know, algorithm is a piece of solution for a given problem which exists independently. When you convert that into any programming language, it is going to stand like a function, right? And these functions can be normal functions, or they can be like recursive also. So coming to that, what a recursive algorithm is, an algorithm which calls itself, that is, its intermediate data is, it is going to use its intermediate evaluations as an input for the next iteration, right? Such an algorithm is recursive in nature. So there are two parts of recursive function, which is base class, and next is the recursive class. Oh, then what do you mean by base class? Base class is nothing but a function which calls the recursive case, right? And the recursive function is the function which calls itself n number of times unless the condition given by the base class breaks, right? Or unless within the recursive call, whatever the break condition you have given, it encounters, right? So these are the two parts of any recursive function. Broadly classified, you can see two types of recursions: direct recursion and indirect recursion. Coming to direct recursion, have a look at the sample which I have given. Example is the name of that function and it is calling itself. Example is calling itself, which will raise a function call of itself. Due course of evaluation, it is going to call itself, and recursively this goes. That is, a function calling itself is a direct recursion. A contrary to that is indirect recursion. Have a look at this example. There are two functions over here. Example 1 is calling example 2, whereas 2 is calling example 1, right? So they are calling each other. It's a mutual, right? And this loop right, is going to break when the breaking criteria gets reached. So this is known as indirect recursion. Have a look at this example once again. Example 1 is calling example 2, whereas example 2 is calling example 1, right? This is indirect recursion. Coming to analysis of the performance. As I said, algorithms are evaluated based upon their friendliness, modularity, sustainability, security, maintainability. All these becomes the key factors which influence the performance. So these are the metrics you can say. Modularity, security, all these are metrics or scale. So we can say that performance is nothing but scale, right? So say for example, you have two algorithms to be analyzed. These two algorithms are the solution for a given problem. So how to analyze them? With same input on two different systems, or two different same system but two different inputs, right? So n number of ways are there to evaluate. So have a look at this one. So first algorithm may work with a given input on one system, and the second may work better on another system with the same input. Okay, so it depends. So asymptotic analysis is a big idea which handles these issues of analyzing the performance of algorithm. Asymptotic analysis. Coming to asymptotic analysis, let's have an example of linear search and binary search over here. We all know that the complexity of linear search is linear in nature, whereas binary search is logarithmic in nature, right? So, if I take, for example, let me narrate you a small story. So, linear search LS is going to run on a faster system, say faster computer, say A. Okay, and binary search is fed to a slower computer, say B. Okay, and then lies and seen that on system A, linear search will give you the result in 0.2 units of time, whereas binary search, even though its complexity is logarithmic in nature, but as it is running on a slower computer, it gives you result in 1000 units of time. It clearly says that the system that a linear search, even though it is working on system A, has given you a very less time, have taken very less time to get executed. So say around, you can roughly say 5000 times faster it is. So for n number of elements or n number of test cases, linear search and binary search will be multiplied by n, the time complexities. Let's have a small look on this one. What is the size of n? What is the performance of LS, linear search on A, and binary search on B? If the size is 10, then roughly it is going to take, say, 10 seconds, and it is going to take around 1 hour, right? If it is 100, it is going to take roughly say 2 hours, and it is going to take some 3 hours, right? When this gets raised 10 per 6, the size of that number of test cases, this will be approximately around 1 year, and this will give you in 5 point, say no, if it is around 10.6, it will maximum will take, it will take 5 hours, and this will take 5.5 hours, and if it raises to 9, it will approximately take 6 years, and this will take 8 hours. See how it raised. As the test cases size you increase, even though the linear search is working on a fast system, it takes much time, and the binary set which is running on a slower system will give you the result fast when compared to the linear system. Okay, guys. So please keep this in mind. It depends upon the size of the input which you are going to give or feed. In general sense, asymptotic notations or asymptotic analysis itself is a weight point. Why? Because generally you think, guys, when you have constructed a database, say for the employees of your firm, there will be maximum around 2000 to 3000. Are you ever going to go for 10 per 9 or 10 per 6 kind of huge amount of people? Definitely not, right? So rather than going deep into asymptotic analysis, you better stick to the basic ones, right? So yes, coming to the analysis, how these and things are analyzed, as I said, worst case, average case, and the best case. So worst case is talking about the case where the things goes worse. That is, if you are thinking of, so for example, let me take an example of insertion sort. Okay, so the worst case will be a case where you are required to sort it in ascending order and the input is in descending order and the output you want is ascending. This will be the worst case in your insertion sort. Coming to the best case. What is the best case? Input and output are the same. Input is ascending and yeah, the output you are expecting is also ascending. This is the best case. Coming to the average case. Average case is nothing but the summation. The summation of all. Summation of all the cases, that is a sigma of I is equal to 1 to n plus 1 theta of n plus 1. Right? So this is going to consider all the cases for n elements and even the case when we cannot do that. That is the worst case, right? So all the cases it is going to take and evaluate and get the average of it. That is nothing but the average case, right? So this asymptotic analysis can be mathematically represented using mathematical tool known as asymptotic notation. And these notations are in 3 different categories: theta notation, big O notation, and omega notation. Coming to theta notation. Theta notation includes both the upper and lower boundaries. It includes both. For example, f of n is the function you are trying to evaluate, then it will be a function of c2 and c1 multiplied to another function g of n, where c1 and c2 are the constants which define the boundary of f of n, right? So theta is the most prominently used one because it considers the lower bound as well as the upper bound. Next is big O notation, where the complexity we are going to consider only is based upon the upper bound, right? Only based upon the upper bound. For example, as they have taken insertion sort, the lower is going to talk about the best case. Am I right? Lower is going to talk about best case. In case of insertion sort, if you are fed with an ascending order and the requirement is also an ascending order, the complexity will be order of 1, which is of no use, which doesn't add any value to the analysis. So why to take that? Why to take that? So keeping that in mind, only worst case scenario, that is upper boundary, is going to be considered for big O notation. A contrary to that is omega, where the lower boundary is considered. That is the best case scenario is considered. So people generally do not go for this one. In the world, we do not expect all things are going to be on line. Never expect that, right? So everything will not be in line. And for example, say if you have $1 million in your pocket and a person says that I have at least $10 in my pocket, then yeah, that is a true point. But how much amount actually he have? $1 million, right? The uppercase is very far. So keeping only the lower case in the mind, we cannot analyze the complexity of any algorithm. So omegas are used very rarely. Most prominently used are thetas. Okay, so let's go with the searching techniques, for which I'm going to show you algorithm as well as a small animation on the same, how it is going to work. Okay. Searching is nothing but a basic operation of data structure where we are going to look for an element and check whether it is existing or not, right? If it is existing, at which position it is. So basically, the searching techniques are divided into two different categories, linear and binary. Coming to the linear search, it is a very, very simple one with a complexity of order of n. We go of n. Okay, very simple. The algorithm says that start with the first element, that is with the index value 0. Compare the element with the key element which you are searching for. If it is not the same one, go to the next element and compare. Go to the next element. Repeat this process unless you find the element. If you reach the last element and check whether it is equal to the key or not, and if it is not the key, just return and say that element not found. Okay, so have a look at this example. So I'm searching for 18 over here. Okay, this is an unsorted list. So first of all, compare it with 21. As 21 is not equal to 18, increment the pointer I. Now I is pointing to 36. Is 36 equal to 18? No. Increment the pointer. Now I is pointing to 54. Even 54 is not equal to 18. Increment the pointer. Now there is a hit. Right? So the element is found at the index value 4. Sorry, index value 3, position 4. Okay. So this is how we perform linear search. Okay. So as I said, index value will be I, then its position will be I plus 1. The next one is binary search. So binary search is a divide and conquer based one. So where I'm going to divide my list, and the prerequisite for this one is the data should be sorted in nature. First of all, the data should be sorted one. Okay, then I'll be dividing the list into two halves, and I'm going to compare my key, the element which I'm searching for, whether it is equal to the mid element or not. Okay, then fine. Have a look at this one. 36 is the element which I'm searching for, right? So first of all, I'm going to sort the list first. So this is the sorted list, and now I have assigned the pointers. Left is the pointer which is going to point to the least index, and R is the pointer which is going to hold the larger index by 2, that is half will be pointed by M. Very good. So the three variables are pointing to three different index values. Compare the element pointed by the mid with the key value. So as the comparison says that the key value is greater than the mid value. As the key value is greater than the mid value, you obviously know that it is on the right side of M. We can clearly forget about the left side. That is, at every iteration, half of the list will be shrinked. So now again reposition left, right and mid. So left is pointing to 2, right is pointing to 4 and mid is pointing to 36, right? So now, yes, the mid is pointing to 36. Job done. Okay, so at index value 3, you found that element. Very good. This is how we are going to perform binary search. That's why linear search complexity, as there are n elements, linear search complexity will be order of n. Whereas binary search is order of log n. Very less when compared to linear search, because binary search at every stage it is going to break the list into two halves. Good. Next one. after moving from searching techniques, we have sorting techniques in hands. Sorting is nothing but arranging the data in any order, either ascending or descending order. We have many techniques for that: bubble, insertion, selection, quick, merge, heap, shell, and loads more. A few of them we are going to look now. Okay, the most prominent one. First one is bubble sort. Here the complexity is very high. Best case is order of n. That is a case where the list is already sorted, and average and worst case are n by n, and it does not use any extra space. So the complexity in space complexity is big of 1. It is stable and in place 1. Data is not going to be moved to any other place, right? So then how it works? The algorithm simply says that compare two consecutive elements, right? That is a simple fund of bubble sort. Let us take an example of a small list of 5 elements. Okay, so compare 21 and 54 first of all. They are in order because 21 is less than 54. Now compare 54 and 36. They are not in order. 54 is greater. So swap them. Once you swap, 54 will be at third position. So compare 54 and 18 now. Even these two are not in order. Swap 54 and 18. Now compare 54 and 29. Even these two are not in order. Swap. End of iteration 1, and you can see that the largest element of it, the list, is in its right position. That is at the highest index value. And this list, the final list which you got by the end of first iteration, will be fed as the input for your second iteration. Have a look. I've converted 54 into blue color because it is frozen. Its place is frozen. Now I'm going to repeatedly work with the same technique for the remaining elements in my list. Let's have a look. Compare 21 and 36. They are in order. 36 and 18. They are not in order. Swap them. 36 and 29. They are not in order. Swap them. Process is done. Second iteration. Have a look at this one. By the end of second iteration, the second largest element is at its right position. Right? Very good. Go with the second iteration by taking the last step of second iteration as the input. So 21 and 18 are compared. Swap them. 21 and 29 are compared. They are as it is because they are in correct order. 21 is less than 29. Now there ends iteration 3 and 29 is in its right position. It is frozen. This will be fed as input for the fourth iteration. Compare 18 and 21. They are in order. 21 will be frozen. Only one item, so no need to compare or do swaps, nothing. So 18 is in its right position. So if there are, keep one point in your mind, guys, if there are n elements in your list, then you are going to do n minus 1 iteration. You will be needing n minus 1 iterations for bubble sort. Okay, so let's go for the next sorting technique, selection sort. It's a very useful one. Bubble sort, even though its complexity is very high, if you have handful of elements, bubble sort will be the best one and a more simple one. Coming to selection sort, it is going to repeatedly find the minimum element. If you are trying to achieve ascending order, it will find the minimum element of the list and it will bring it to the front end, right? And the best and average worst case scenario is we go off n into n, right? And the memory, it is not going to use any extra space. By simply swapping the data, it is going to sort the list. Right? It is a stable and in place one. Coming to the logic of selection sort. So start with the first element and we search for the smallest element, bring it to the first position. Now start with the remaining list, search for the second largest one, bring it to the second position, and we are going to repeatedly do this unless we reach the end of the list. Right? Have a look at a small example of the same. So I is the index value, I value. J is going to hold an index value which is 1 plus the ith, and M is going to point to the same. So I can say that I and M will always be pointing to the same, whereas J is a step ahead of I. Okay, compare. If the element pointed by M is greater than the element pointed by J, then shift the position of M. Here the element pointed by M is 21, J is 54. 21 is greater than 54, fails. So just increment J. So once I increment J, J is pointing to 36 now. Now again do the same process. Element pointed by M and J. 21 greater than 36, condition fails. Just increment J. Now J is going to point 18. Now again compare. 21 greater than 18. Condition satisfied. Now M is going to point to the J and J will be incremented. Right? So the result will be, so M is pointing to the third index and J is incremented and it is at 29. Again do the same process. Okay, is M, the element pointed by M, greater than the element pointed by J or not? 18 greater than, no, the condition fails. And if you increment J, J goes out of boundary. So this says the end of first iteration. When you reach the end of first iteration, swap the content of the elements pointed by M and I. Okay, that's what I have done. So 18, the least value of the list, has come to its first position, right? Or the 0th index. Okay, let's start the same process with the remaining list in your hands. Okay, so now I is initialized with index value 1. Same, M also initialized to index value 1 and J is initialized to the next position of I. Start comparing the elements pointed by M and J. So here 54 and 36, condition satisfied. Change the position of M and increment J. So the resultant will be like this. Again compare. 36 is greater than 21. Condition satisfied. Change the position of M and increment J. The result is like this. Now again compare. Element pointed by M is 21, is less than 29. Condition fails. Simply increment J, which goes out of limits, which tells you that this is the end of the second iteration. Swap the content pointed by I and M. So that is swap 21 and 54. So this is the end of second iteration. Coming to the third one. This is I and M are going to point to 2 and J is going to point to index value 3. Now compare the content. Is 36 greater than 54? No. Increment J. So now J is going to point to 29. Is 36 greater than 29? Yes. Move the position of M and increment J. If I increment J, J goes out of boundary. So swap 29 and 36. Now this is the final list. 54 and 36. Now I and M are going to point to 54 and J is going to point to 36. Is 54 greater than 36? Yes. Change the pointer of M and increment J, which goes out of limits. As it goes out of limits, swap the contents pointed by I and M. So 36 and 54 are swapped. If I increment J, it says that it is going out of limits. Remember, here I is going to run from index value 0 to n minus 2 if there are n elements in your list, and J is going to run from 1 to n minus 1. Right? So if I increment I, it goes out of boundary because I have an axis of I from index value 0 to 3 only over here. Right? It gets exceeded. So this, whenever I goes out of limits, it says that it is the end of the logic. Right? And the final list is the one, the sorted list. This is selection sort. A contrary to that is insertion sort. Insertion sort, we are going to pick the largest element and put it in the last. Is it's at every iteration is your insertion sort. Let's have a look at an algorithm of the same. So this is the list. So we are going to go in a reverse order, right? So I is going to be positioned at the first index and j will be one step behind it. As I said, it's a different one compared to selection, right? So compare the key element, that is the element pointed by I and the element pointed by j. If the condition fails, then place the key in j plus 1th position. So as the condition failed, I have placed. Next, the key is pointing to the element pointed by I, which is 36, and j is one step behind it. Compare the key and the j pointer element. So if the condition 36 is less than 54, condition satisfied. As it is satisfied, now place the jth element, that is 54 in j plus 1. That is overwrite 36 with 54. Right? Now, take the key and compare. Now with the new elements, the 36 is less than 21, condition fails. As the condition fails, just copy the key into a j plus 1 position. Reinitialize. So I is pointing to index value 3 now and j is one step back, and key will be holding the element pointed by I. Now compare the key with the jth element. So 18 is less than 54, condition satisfied. If this condition gets satisfied, overwrite 18 by 54, right? And decrement j. Now j is pointing to 36. Again compare. So 36, 18 is less than 36, condition satisfied. Overwrite 54 with 36, right? So the list will be like this. Now j is pointing to 21. Is key 18 less than 21? Again the condition got satisfied. Overwrite 36 with 21, right? So this is the current scenario. If you further decrement j, it goes out of limits, which says that out of boundary. So overwrite the content in j plus 1, that is 0th index with 18. So the first element is in its right position, right? So now I is at 29, j is at 54. So the same process you are going to repeatedly do until unless the list is sorted and I crosses the boundary, right? So condition satisfied, 29 is less than 36. Copy the content, right? Again, j is decremented, 29 is less than 21, condition fails. So key in j plus 1 position. Then again, key is 29 is less than 21. End of the logic, right? As the when you increment I, it goes out of limits. I is going to run from 1 to, here the limits are, I is going to run from 0 to, it is going to run from 1 to n minus 1 if n is this size. And j will be running from a step, it will be one step behind till 0. It is going to take back steps, whereas j is going to take forward steps. If once I is the main point over here, if it cross its boundary, it is the end of the logic. If j cross the boundary, it is the end of iteration only. Okay, right. So this is your basic selection sort, right? These are the 3 basic sorting techniques which we have. And guys, you can watch my remaining videos where we have given a clear picture of how quicksort works, merge sort works, and heap sort works, with a brief introduction of algorithms. And in a heap sort, we have explained what a heap is, what is a minimum heap, maximum heap, and how to heapify the data. Right? So this was a small introduction to data structures and what an algorithm is, how it acts as a backbone for a program, right? And what are the factors which influence an algorithm, followed by 2 searching, and 3 sorting techniques. I hope this video was effective, and do follow my channel. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.